Nuclear magnetic resonance spectroscopy, or NMR spectroscopy for short, is a fantastic tool for working out the shapes and the structure of molecules, and it's one of the most useful analytic techniques and one of the most powerful ones that you can have in organic chemistry. But before we understand how to interpret it, we've got to understand what it actually is. So oddly, I'm not going to start off talking about the nucleus. I'm going to start off talking about electron shells, because you have come across a property before called spin, and I'll remind you of that. If you have, say, a carbon atom with 6 electrons, then when you work out the electron configuration, you think about the s shells and the p shells, you say, right, okay, well, we've got 6 electrons, we're going to put 2 in the first shell, in the s subshell, and then we're going to have 4 left. We'll put 2 in the s subshell of the second shell, and then we'll go, right, okay, 3, 4, 1, 2, 3, 4, 5, 6 electrons in carbon. And you'll notice here that we've got 1 arrow up and 1 arrow down, and you may remember that that's because the electrons have a property called spin. And we say that if one is spinning one way, the other one will have an opposing spin and spin the other way. And electrons have this property called spin, and they're not the only things either. In the nucleus, nucleons, protons and neutrons, also have this mysterious property of spin, and each nucleon will spin in a certain way. So let's look at the hydrogen nucleus. That will have just a proton in it, and that will therefore have a spin in a certain direction, and therefore we have an overall spin in a certain direction. Now, if we think about deuterium, deuterium has 2 nucleons. It has a proton and it has a neutron. Now, I have got the proton and the neutron together. The spins will oppose each other, and so overall there will be no spin. If we take tritium, we have 1 proton. The second neutron I'm going to put in has an opposing spin to the first one, like I did before. And if I take a third nucleon, then it's got to go one way or the other, and so therefore we will have overall a spin in a certain direction again. Alright? And then finally, helium have 1 proton, 2 protons, 1 neutron, 2 neutrons. Because we've got an even number of nucleons, 1 up, 2 up, 1 down, 2 down, we will have no overall spin. So certain nuclei have an overall spin, and those are the nuclei with an odd number of nucleons. So the most common ones are hydrogens, which are just 1 proton, and another one would be carbon-13, which has 6 protons and 7 neutrons. So they cancel, each pair of nucleons cancel each other out, except the last one, which will then give you an overall spin. So with NMR spectroscopy, we're going to use this spin to create some sort of measurable effect on a molecule. I'd like you to imagine that I have a magnetic field north to south, and I'm going to put in the middle a bar magnet, and the bar magnet will attract to the magnetic sides. If we call these magnets, then the north end of the magnet will attract to the south, and the south end of the magnet will attract to the north. But if I put it in like this and I let it pivot freely, then actually it will spin itself back. But it won't go directly there. What it will do is probably actually spin itself back, overshoot and wobble a little bit like this. Okay, and so what I'm doing is I'm putting energy into this magnet to turn it against the magnetic field, so it's repelling and repelling on both ends, and it's going to spin round back again, and then it's going to do a little wobble. Now that's kind of like what's happening to our nucleus with uneven spin. If I put a nucleus of uneven spin into a magnetic field, I can turn it round against the magnetic field, and it will flip back and it will wobble. Don't tell any physicists I said wobbling. But what's happening here is we are getting a kind of like an oscillation, and we can measure how much energy we get from that, like this. So if I have my nucleus aligned against the direction of the magnetic field, then we have a high amount of energy. If it is aligned with the magnetic field, then we have a lower energy. And so the difference in energy there is what we're going to measure with NMR. Okay. So how are we going to turn it around to this high energy state? Well, what we're going to do is we're going to take some radio waves and we're going to zap the nucleus with the radio waves, and that will align it against the magnetic field, and then it will turn back, and as it oscillates it will actually give out radio waves of a slightly different frequency. And what we can do is we can measure those radio waves. The more of a difference there is between here and here, the bigger the energy gap, and therefore the higher frequency there is of the radio waves. So what we're doing is we're measuring how different is this nucleus when it's this way round compared to turning it against the field this way round. So what affects that strength? Well, the nucleus isn't alone, and what the nucleus has around it, of course, is it has a cloud of electrons. Now when you're thinking about this cloud of electrons, they are obviously in their shells, they are all around, but they also do have spin. So when my atom encounters the magnetic field, the nucleus is actually to a certain extent shielded from the magnetic field by electrons. And the higher the electron density I have around here, the more shielded it will be. And if it's more shielded, the effect of turning it in the magnetic field is not going to be as energetic. It's going to be protected against the magnetic field, so when it's this way round, the repulsion, if you like, is not quite as strong. So it's not going to turn around with quite so much back to align with the field with so much energy. And so if I have something really electron dense here, we get less of a gap and therefore a lower frequency of radiation given out. And if I have electron deficient atom, where the electrons are being pulled away by electronegative atoms or something like that, then we'll end up with a really high difference in energy when we oscillate the nucleus, and that means that we're going to get a higher frequency. So we can print this out. We can print this out in a graph, if you like, and we, across the x-axis, have the chemical shift represented by a little delta, and we measure that in parts per million, ppm. And we can measure how much of a signal we get at each radio frequency. Now we need to know roughly where to start measuring from, so you see I've marked 0 here. We put a special chemical in called TMS, and that will always give the same signal, and so we always say that that is the signal that we expect at 0. So we'll get a little peak at 0 where we've put in this reference material. Okay. Now the chemical shift of the rest of the molecule that we've put in will depend on how much electron density it's got around it. So electron dense atoms tend to end up here, and they'll give us a chemical shift in the graph up here, for example. And electron deficient atoms will show up down here. And so by studying how far away from the initial reference a peak is, we can work out what kind of atoms must be around that particular atom. And what we also find is that different atoms occupy different parts on this scale anyway. So if we zoom in on only the kind of range that contains hydrogen, we can see only the hydrogen atoms on one sketch. And if we zoom in on the range which says just carbon atoms, we can say, okay, well the carbon atoms, all these peaks are due to carbon atoms. We can examine the individual carbon atoms, and therefore we can examine the environments that you find each atom in, and say, well, what is making this more electron deficient, what is making this more electron dense, and we can work out the bonding around that atom, and therefore we can find lots of really useful information about the structure. More on how to interpret that later, but that's basically a brief overview using lots of analogy and quite a lot of shortcuts of how it works.